Okay, moving on to question 5 of the halogen derivative tutorial. Okay, in question 5 we are looking at synthesis. So if you recall what is synthesis question, typically we give you a starting reagent and we say that, can you propose a series of steps to get to B, the product? Alright, then you're supposed to propose various steps to get to the compound you want. So it can be 1 step, 2 steps, 3 steps, multiple steps. Alright, so in halogenal alkanes, we are going to look at more additional reactions, and therefore you expect the demands of synthesis question to be higher. So before I go into that, I just want to make use of the guidelines that we gave you guys so that you understand how to what it means. Okay, so typically when we see the starting reagents, for example, starting reactant is A, maybe it has a 4 carbon, and then to B later on when we have a 5 carbon chain. This type of reaction is where we have an increase in the number of carbon atoms. This is what we consider a step up reaction. Okay, a step up reaction. And so far, based on what you covered, this is one thing that you realize that will result in a step up when you replace your halogen with ethanolic KCN. Alright, ethanolic KCN, heat, right, under reflux, you get R-CN. You notice that there's one additional carbon. So there's one additional carbon. Now, this part about carbonyl compounds using co-alkaline HCN, this is something that we'll cover in the topic of carbonyl compounds, so we not to worry on this, we will teach you. So these are the two reactions that result in what we call a step-up reaction. Okay, now what happens if we have a decrease in number of carbon atoms? Of course, conversely, we look at a step-down reaction. Okay, when there's a decrease in the carbon atoms. So an example of a reaction, a step-down reaction that you learn is on the an example of a step-down reaction that I've learned is the oxidative cleavage of the CC double bond of alkene. So if you cannot remember this, let's just take a look at a simple example. So for example, if I have a terminal alkene, alright, terminal alkene, and I will do oxidative cleavage using KMNO4. Alright, you know that this portion here, terminal alkene, will become CO2, right? And then you end up with a CO, and then whatever compound. You realize that based on that, because you have lost this carbon, you therefore decrease the number of carbon atoms. Okay? So you have a step-down reaction. So if you notice your starting reagent and your end product, there's an increase or decrease in carbon, then you know that if it's increase in carbon, then you need to consider this. You need to have a halogenal alkane, then you use ethanolic KCN. Now if you notice that a decrease in carbon, then you need to convert it to alkene, then you do your strong oxidation. Now, iodoform test is a topic that we will learn in alcohols, so that will be covered in your SLS lecture. Okay, one thing that I need to highlight to you guys is, if there is a change in the position of the functional group, you can either consider a series of elimination followed by addition reaction or addition followed by elimination. This is difficult to understand. I will explain this using 5A part 2. Okay, now for a general rule of thumb is that for complicated questions, alright, it may be easier to start from the final product and work backwards. So we think backwards to the reactant. Okay, so I'll show you an example of what we mean by thinking backwards through 5A part 1, and we try to propose the least number of steps and to have high yield. So typically in a synthesis question, we will not try to propose free radical substitution, because free radical substitution, it's a reaction that results in multiple side products, and therefore the yield won't be good. Okay, so let's take a look at 5A part 1. We have an alcohol, ethanol, to a dibromoalkane. First of all, first thing to check, 1 carbon, 2 carbons, 2 carbons here, 2 carbons here. Right, there's no change in number of carbons, so no need to do step up. No need to consider ethanolic KCN, no need to consider oxidative cleavage. Alright, there's no change in carbons, okay, that's good. The question is then, how then do I propose? Alright, so in this case, because there is no clue given in terms of how many steps, and we know that we can convert the OH to a BR quite easily by using PBr3, for example. But there is no reaction that converts OH and H to both BRs at the same time. So definitely it won't be one step. So now if you find that going forward, example alcohol, converting to dibromo is difficult, you can only convert single bromo, then you realize, okay, that's not going to be a good way. So that's why I'm suggesting you guys to think backwards. Now, think backwards. What do you mean by thinking backwards? I have a dibromo alkane, and we know that a dibromo at position 1, 2, that means adjacent to each other, can be easily obtained if I have an alkene, right? So you think about it. If I have an alkene, I can easily add 2 Br atoms across the CC double bond, right? Just adding Br2 and CCl4 in the dark, I can have electrophilic add. And that's how I can get my dibromo alkane. Alright, so now I'm thinking backwards. This is what I mean by thinking backwards. I have an alkene. Then I see if I can link this alcohol to this alkene. Then I realize it's possible because I can eliminate out this water to get an alkene. And therefore I conclude this is going to be my synthesis pathway. All you need to do is to propose the reagents and condition to bring an alcohol to an alkene to a 1,2-dibromo alkane. Okay, so in this case, let's take a look. How do I do elimination for this? For alcohol, I can use excess con H2SO4, heat. Alright, or I can use excess con H3PO4, heat. Or I can use Al2O3, heat. This will bring about elimination reaction from alcohol to form an alkene. Then once I get my alkene, to get my dibromo product, all I need to do is just Br2 and CCl4 in the dark. Why in the dark? To prevent free radical sub. And this is our electrophilic addition reaction. Okay, so now that you have a clue of what you mean by thinking backwards, what are things to consider, number of carbon atoms, can you try to do part 2 on your own first before going on with the next part of the video? Okay, again, synthesis is a question that you need to exercise your thinking process. Okay? Okay, with that, let's take a look at part 2. In part 2, first of all, let's take a look at the question. How many carbons do I have? 1, 2, 3. 3 carbons. In this case, how many carbons do I have? 1, 2, 3, 4. 4 carbons. So, from a 3 carbon to a 4 carbon, there's a step up. A step up reaction means I need to consider using ethanolic KCN. And I know that if I use ethanolic KCN, I will have a CN group in my compound, right? And I know that the CN group can be easily converted to COOH. So let's, for example, we think backwards from this compound. Okay, we will have a compound that looks something like this, right? CH3, CH, CN, CH3. Right, because the CN here can be easily converted to COOH via acidic hydrolysis. Right, so I say again, this CN can be easily converted to COOH via acidic hydrolysis. Now the question is, how can I get this CN then? To get this CN, it will mean that I must have a Cl or a Br halogen on carbon number 2, right? But now you take a look at this. My Cl is on carbon number. My Cl is actually on carbon number 1. But I need the Cl to be now at carbon number 2. So, which means I need a reagent that looks something like this. CH3, CH with a Cl on carbon number 2. And then I can do my nucleophilic sub, replace the Cl with a CN, ethanolic KCN, heat. Alright? So the question is, how can I change my Cl position from position 1 to 2? Remember the tip I shared with you earlier on at the start of the video? Now consider elimination followed by addition. So let's now take a look. What happens when I eliminate this? If I eliminate this, I will get an alkene. The Cl is gone with the adjacent carbon hydrogen, I get a double bond. Alright, can I get this compound from the alkene? What do I need to do? If you compare between this alkene and this compound, the main thing is I need to add a Cl, I need to add a H. So when I need to add a H and a Cl, basically it's adding HCl across the CC double bond, right? So can I do that? If I add HCl across the CC double bond, it's electrophilic add reaction. My H is my electrophile, right? H is my electrophile. The H following Markovnikov rule will be added to this carbon with more H. So add this carbon, you have CH3, the Cl will be in this carbon. So you can see a series of elimination followed by addition reaction will result in a change in the position of the Cl group. So now with that, let's take a look at the suggested solution then. Alright, it's possible to get this compound Okay, so first of all, let's take a look how to chemically get alkene. We use elimination, ethanolic KOH or alcoholic KOH heat. Then to add HCl, of course we just HCl gas and heat, we have electrophilic add. Converting the Cl to a CN is a nucleophilic subreaction. We use ethanolic KCN, heat under reflux. That's the compound we get. And to get the CN, alright, to get the CN to the COH, basically we do acidic hydrolysis HCl, heat under reflux. Okay, so this is how you think backwards and you think forward. Okay, so this is a series of skill sets that you have to use. First, check the number of carbons, consider the step, look at what are the analogous component, the COH analogous to CN because it can be easily converted via one step. And then you think back what CN is analogous to Cl, which means the Cl must be at position 2. And this will indicate that you need to consider eliminate followed by addition to change the position of the Cl group. Okay. Okay, with that, I'll be recording 5B in a separate video.